So the topic of my presentation is Bharat Vandana Park, New Delhi. I'm representing Eckersley O'Callaghan, short form EOC. My presentation is split into three parts. EOC is a design consultancy firm. This slide shows our footprint on the world, 11 offices, headquartered in London, 28 nationalities, and 67% of our work comes from repeat clients. Sorry, just a minute. So EOC India was set up in July 2021 to build a solid portfolio of exciting projects in India. Our business is split into three consultancy verticals: structures, facades, and glass. The image on the extreme right is the latest EOC engineered Apple store, that is Apple Store BKC in Mumbai. EOC is a glass specialist. Its genesis is closely linked to its association with Apple, which spans 19 years and 350 plus Apple stores. Now I'll introduce the project quickly. Bharat Vandana Park is a district park located right next to Delhi Airport. The plot size is 900 meters by 900 meters. EOC was tasked with the structural design with a star of two signature elements in this project: a unique 1.2 kilometer cable stayed footbridge and 9 45-meter tall pylon systems. The red line on the master plan is the alignment of the longitudinal alignment of the footbridge. Now, if you look at the various elements of the footbridge, this is the deck, 1.2 kilometer long, 4.2 meter wide, 18 meters above ground. It's made from welded steel plates, and the cross-section varies along the length. There are 9 RCC pylons which support the deck, and they are very slender, diameter 4.5 meters. There are 9 45-meter high steel diagrids with diameter 20 meter at the base and 44 meter at crown level that wrap around the RCC core. There are steel cables, fully lock coil cables have been recommended because of their high corrosion resistance in Delhi environment. Diameter varies from 40 to 52 mm, and the length of the longest cable is 76 meters. The total length of cables is approximately 8 kilometers on the project. And the white picture is the cross-section of a fully lock coil cable. So the last element of this footbridge is 2 discs which connect the diagrid to the RCC core, and this together forms a pylon system. This is the global layout. Total length of the footbridge is 1200 meters. There are 9 pylons, 8 spans. Right, so that's... Now, the third part of my presentation is about, it's related to today's theme, which is 7 minutes, 7 ideas. So I'll touch upon 7 bullet points that are relevant to this project and this event. How do we make an informed decision in concept stage? I can give you a few examples, like the longitudinal alignment of the footbridge. What if I change it slightly with respect to the pylon locations? What happens to the flow of forces? Or if I take the pylons in and out with respect to the footbridge, what happens to the flow of forces? Now, these are some decisions which are very critical because they define the course of such a project. So how do you do that in a concept stage? The answer is programming or parametric design. Today morning in the keynote sessions, this was already highlighted. So rhinoceros, caramba, and grasshopper is one solution to this. In short, parametric structural engineering. The advantage is that in a single software environment, you can have the geometry, you can do iterations, and you can very quickly see the results and make some informed decisions about your project. And it's very critical at the, again I'm repeating, at the concept stage, because that is where any such scale project gets a direction. And if the direction is wrong, then everyone knows what happens. Second point is some system details. You can see that end span 1 and end span 2 are close to the pylons, and there is a midspan. The cables switch sides at midspan. At end spans, the bridge is laterally and torsionally connected to the pylon. And at the midspan, there are movement joints. On the top right, you see the cross-section, how it varies from end span 1 to middle span to end span 2. So that's why I said in the one of the earlier slides that the cross-section varies along the length of the bridge. This is because the cables are switching sides at midspan. That's why this design is in such a way. Again, if you go from left to right and top to bottom, you see how the bottom apex of the cross-section is shifting towards the right. It reaches the center. Then for the next half span, it follows the same but in a mirrored way. So the third point, is about how that you should put in efforts to save steel. So these colors on the slide are basically tubes of different cross sections or tubes of same cross section but different wall thicknesses. So it's better to group them as per the structural requirement. But too much of grouping is also bad because steel suppliers have minimum tonnages which they need to adhere to. Then another way of reducing steel consumption is using stiffeners for plates. If you have a 14 mm thick plate as the structural requirement, you can reduce your consumption of steel by using stiffeners, and maybe your plate thickness comes down to 10 or 12. Fourth point, get the right wind load. So on the left, you see a render of the pylon. The rhomboids that you see on the diagrid are stainless steel leaf patterns. Basically, the architect wants to show this as a big tree. And on the extreme right, you see the wind tunnel test model. Now, why do I say get the right wind loads? It's very important at the beginning of the project to be clear with the wind tunnel consultant. What loads do you want and in which format? Do you want the components and cladding load, or do you want the main wind force resisting system loads, or do you want both? Again, wind tunnel testing is a costly measure, so every effort should be taken to keep the communication clear at the starting point. Point number 5, give a thought to fabrication in early design stages. When we got this starting geometry from the architect, the angles were hayway, so there was no possibility of grouping the angles, but with some in-house analysis tools, we found out that the angles are within a range, and if we slightly tweak the geometry within the architectural bounds, we can have groups of angles, which ultimately pays off during fabrication because you have repetition. Yeah, last point. Then give a thought to fabrication again, if you can group lengths of tubes. 6th point, give a thought to construction sequence in early design stages. Because let's say in this example, if you load the footbridge on the RCC core only and then install the diagrid, then the deflection under dead load of the RCC core is 163 mm, but because it doesn't have the diagrid with it. But if you install the core and the diagrids first and then load the bridge, the deflection is reduced by half. So the construction sequence is very important, and it has to be freezed at the beginning for such projects. Last point, everyone wants the GFC drawing set, but no one wants to talk about the steelwork specification, which is very important. I think it should be given higher importance than a GFC drawing set, because we want structures to last long and not rust in 10 years. So these categories, AESS 4 is the best. 1 is the minimal aesthetic requirements. And as you can see, 1 is not that aesthetic, 4 is very polished. Now a contractor wants 1 and a client wants 4, but both have to work out somewhere in the middle, which is where you can categorize exposed steelwork for quality cost balance. Members that are exposed to naked eye can be a higher quality category, and the others which are far from the naked eye can be a lower 1 or 2 category. Thank you very much.